Hello, welcome, and an excellent evening. This is an update to the linear voltage regulator versus switching voltage regulator video that was relatively popular on my channel. And let me talk you quickly through what we learned in the last round. For several decades now, these metal can linear regulators such as this 7812 or this 7805 or the venerable LM323 have been used to regulate voltages down from, let's say, I don't know, something like 14 or 15 volts for the 12 volt regulator down to the 12 volts stable output, or something like 7 to 9 volts DC down to 5 volts with a 7805. They are working really well. They produce nice, clean, stable output up to 1 amp or 1.5 amps. I think there are some 3 amp versions even. However, they have one drawback. They boil off the excess voltage in the form of heat, so they can get pretty hot. And especially on the older Commodore 8050 and 4040 dual disk drives, they have 3 of these inside, and they can get pretty toasty. And some of those also fail. I think the pinball community has had lots of failures because their devices are running much longer than your usual floppy drive, being turned on for 12 hours or more a day for years on end, so they will see failures. In the Commodore disk drives, I've never had one fail. The bridge rectifiers, yes, but these ones, no. But they do put out a lot of heat. You can also find these in the original 1541 disk drives that are very popular with the Commodore 64 and similar machines. They have 2. They have one 7805 and one 7812. So what are you going to do if you want to have your machine running cooler, or if you want to replace a failed thing? Well, the company called ezSBC.com has had these nice things, the PSU5 and a couple of other variants, for some time now, and they are switching regulators, and they are very popular in the pinball community, and they seem to work fine for them. However, they have one drawback. Switching regulators produce ripple. These here are DC regulators. They take direct current, not alternating current, and regulate it down. And direct current means it should be like a straight line on the oscilloscope. No wibble or wobble whatsoever, because it's not alternating current. But the switching regulators, due to their switching nature, will produce ripples on this DC signal. And for some applications that doesn't matter. For example, the 12 volt regulator here is usually used for the stepper motors. And if you have a ripple of 100 or even 200 millivolts, it doesn't care. The stepper motor will still function, and the spindle motor as well. That's no issue. But for some logic ICs, and especially for analog electronics, like the one in the read-write heads of the 8050, it's actually pretty bad. I had my 8050 repaired, and it was working incorrectly. It was having read errors on one drive. And it turned out it was due to this regulator producing too much ripple. I replaced all 3 linear regulators for switching ones because the 8050 runs so hot. Well, along comes Mr. Floppy from the DOS Reloaded forums, and he said, hold my beer. Came back after a week or so with this design here. Yeah, which is a super low ripple voltage regulator. This is the better version, basically version 0.1, as you can see here. And this one is actually jumpered for 12 volts, but I do have 5 volts variants as well. And it comes with this surface mount coaxial socket for measuring. with a Z0 probe, which I have lying over here. So this plugs into this thing here. And then you can directly measure with your oscilloscope with 50 ohm termination, like a 20x probe without any big issues, without great ground loops or anything, which is good. This, of course, was the beta version. It already was super clean, super nice output, running very cool, being a drop-in replacement for the 7812 or the 7805. And this year, he came up with a revised version. You can see it looks very similar. He got rid of the little coaxial connector because not being a better version anymore, it doesn't require that. The inductor got a little bit bigger, probably for some reasons that I can't explain. But other than that, it looks very, very similar, it seems. I'm not an expert in these matters, so you have to ask him if you want to know more. And I think this resistor at the top left is probably for adjusting the output voltage, which here is populated for the 5-volt variant. Yes, it is open source hardware. I'm not sure that the Gerbers and schematics are already out there, but they eventually will be. It's revision 0.2. It even comes with a nice data sheet, drop-in positive switching regulator, etc., etc. It says all kinds of things. EMI filter buck regulator, EMI filter E-fuse. Has the electrical characteristics, can produce between 8 and 26 volts on the output, it seems. Interesting. Oh no, it's on the input, of course, 8 to 26. That makes more sense for the 5 volt and 15 to 26 on the for 12 volts. Yeah, current up to 3 amps, below 40 degrees Celsius, and below 60 you can go up to 2 amps. So it's pretty beefy actually. There's the trip current for the E-fuse, soft start time of 68 milliseconds, so pretty quick, I guess. I'm not sure how fast the original linear regulator is, if it also ramps up, but maybe we can test that. Yeah, question would be how can we trigger that? Probably on the V in, I guess, and then watching for the V out. That would be quite nice, I guess. Something to the dimensions and the assembly, installation, etc. Probing. Yeah, some probing inputs for the package here. And he even designed this board here, which is called the checkerboard. And there should be a nice heatsink on there to dissipate the heat for the linear regulators. I think these ones here don't need that. They have not that high of dissipation. I have one on order, but it hasn't arrived yet, so I will run this only for very short amounts of time. It's a 7805, so it will produce some heat. I have hooked it up to a 22 ohm power resistor, which should give us, let me check, 20 ohms, 22 ohms should give us roughly 1.1 watts of dissipating heat. So it will get a bit toasty, current of 0.22 amps, but it shouldn't run too hot, I think. And 220 milliamps is in the order of what, like, I think a regular 1541 board might take up. At most 400 milliamps, I think, is something you would see on those things. They definitely don't max out the 1 amp or anything like that. So yeah, this is probably also getting warm, but nothing to worry. This is rated for 50 watts, and this is far from that. All right, I also attached the Z0 probe here. I don't have a second terminator to attach another Z0 probe on the input, but I've checked my Voltcraft lab power supply. It has very smooth output, no visible ripple. In fact, I do have quite a bit of noise when measuring like that, and I'm very interested and curious to see if we can pick up anything above the noise level, basically. So this is currently mounted in here, attached with two little bits of solder. You couldn't see that. So we can have one first measurement using the linear regulator, and then we will have a look at the ezSBC one and the previous iteration, if I can find a 5 volt, that is. So we have similar setup, but I don't think I have, so we might have to skip on that. But anyway, yeah, I think I do have one still in here. Yes, this is a 5 volt previous revision, so we can test that and compare that to the other one. I probably assume you won't see any difference between those two. But the trigger board is very nice. I've hooked up the input here. We are only pumping something like 200 milliamps through there, so the thin wires should be enough, I hope. I don't have any beefy wires right here, right now. But yeah, we will see if they start smoking or anything, but I doubt that. All right, let's turn on the scope and the lab supply and see what it gives us. All right, so the scope is on, as you can see. It is switched to a 20x probe, bandwidth limited to 20 megahertz, as is usual for these kind of applications, and coupling is set to AC, which means we have a nice line down here. We are at 20 millivolts per division, and there's only noise visible. So this is really just the background noise, which I can probably influence a little bit by moving around the components. But this is basically the measurement noise that we are dealing with. And if I switch on the power supply, I see 240 milliamps as expected. And the scope has to ramp up, I guess, and filter out the AC component, and that takes a while. So yeah, it will be very hard to measure the on time, basically. Probably impossible for me. And everything is pretty cool to the touch. This here gets slightly warm, but less than hand warm. So it does seem to work. You don't see anything different here. The voltage peak to peak is still the noise floor, basically. My scope isn't good enough to pick up on that. I do have the termination on here correctly, so everything should be fine. And there's no visible difference, I would say, in the signal here. There is something that we can pick up at about, let's see if we can trigger on that, probably way too low. This is way too noisy. We're on 5 nanoseconds. This is, I don't know what kind of noise this is, probably from my lighting or anything. It's nothing that you can actually discern. Now we are 20 nanoseconds. There's no particular noise that is being generated by this linear regulator, because it can't. Maybe it's also from the switching lab supply or something. I don't know how that works. But as you can see, this is as clean as you can get, more or less. If I turn this off, the signal is still there. So I would say this is probably from my lighting, from the LED lighting, etc., which is being picked up from the surroundings. Okay, that's this regulator. Let's try and swap this out for the ezSBC. So the PSU5 from ezSBC is in. Slightly wonky, but there's a ground connection. I checked everything. Everything is good. The legs are a little bit too thick. Mr. Floppy had the idea to install pogo pins on these, but I don't have any pogo pins, so we don't have to desolder all the time. And the through hole gets narrower and narrower. So I just stuck them in, put some solid solder on there, and used a standoff to get that there. But yeah, setup is a bit wonky, but that does not influence the measurement quality in the least, because you can check yourselves. The scope is ready. The multimeter is here for seeing what the actual output is. We're gonna switch on the lab supply and we have 5.17, so roughly 5.2 volts, which is fine. You can dial that down here on the control board. And we already see a much higher ripple, or ripple at all. Voltage peak to peak here says 100 millivolts, which is roughly what we are seeing here. We have 40 millivolts per division. It goes a bit to the negative and roughly 2 lines above, so that's 80 plus a bit of change, so somewhere around 100 millivolts. That's 20, that's, what is it? That's roughly 2% variation. Doesn't sound like much, but in some applications that's too much. So yeah, the frequency is around 630 kilohertz, it seems. That must be the switching frequency. It's also not super stable. I guess it's probably also oscillating a little bit to not have like a regular like mode of resonance or something like that. I don't know. I do know that I think this regulator, the Mr Floppy regulator, does randomize the switching frequency, so probably this does something like that as well. I'm not sure, but it seems to be around 600 kilohertz. So yeah, not terrible, but also not great. And it seems that this is already enough to get an analog floppy drive to go all crazy. So next up, I'm going to put in the new revision. And if we have some time left over, let's say, I will also try to put in the older revision, but I think there will be no big difference. So let's swap that out. The Mr Floppy regulator's in. I set up this time with 2 hex standoffs and used some resistor legs that I cut off to feed through the through holes and solder it to the leg. So the desoldering is very simple. Heat dissipation is of course an issue in this configuration, so we won't run it for long, but it should not dissipate that much heat anyway. The scope is again in our usual arrangement with AC coupling, 20 megahertz limit and 20x probe. You see the usual noise floor, and I'm now gonna turn it on. And we get 5.042 volts, pretty bang on, I would say, a perfect 5-volt regulator. And we see roughly 20 to 30 millivolts peak to peak at this scale of 5 microseconds, which is, I think, pretty acceptable. The frequency is all over the place, I would say, which is also good, I guess. Looking down to the nanosecond level, we just see the noise. So yeah, I think this is exactly what we were expecting. Basically, this is roughly up to 5 times less ripple, much less pronounced, definitely. The spikes are much smaller on this level. Let's see if we ramp up the resolution. I can't go further than 20 millivolts per second, so that's where it ends. Yeah, it's now counting at 167 kilohertz, but you see that the frequency seems to be all over the place. But yeah, basically this is really low ripple, and especially good enough for the analog properties of the floppy drive. So that's pretty neat. Everything is running cool so far, I would say. Looking pretty decent. Output seems to be at 160 milliamps, which is interestingly very low, lower than I would expect. However, we do have 5 volts at the resistor over here that you can't see. The jumping around is due to the quite loose connection of these crocodile clips. Interesting. So with the linear regulator, we saw roughly 240 milliamps, and I would have assumed that we would get, what did I say? Let's check with the calculator. I would have assumed to see 220 millivolts, milliamps roughly, which is lower. Weird. But maybe my voltcraft is different. Oh, it might be just more efficient, right? At 8 volts, it only draws 160 milliamps. That is, of course, a possibility. This was slightly higher, and this was the highest, having the biggest heat dissipation, obviously. But there you have it. That is the brand new Mr. Floppy version 0.2 voltage regulator. I will link to the forum post. It is the DR340 and DR78XX series drop-in positive switching regulator version 0.2, as I said. Very neat and very lovely. The checkerboard is quite useful for evaluating these. And yeah, I think that pretty much sums it up. A great product has become even better. I'm looking forward for this to even become open source, real open source hardware with all the schematics and everything supplied. But other than that, it might be possible that Mr. Floppy will sell them somewhere, either on the forums or officially, I'm not sure. This kind of stuff is usually quite a lot of work to do the sales, etc. But if he does, then I can thoroughly recommend these for your vintage floppy drives, pinball machines, and all kinds of other stuff that uses the old TO3 package linear regulators. It's definitely an excellent replacement, and I guess there will be only very few applications where this won't be an option compared to the old metal cans. I do like the look of the metal cans, but as these things are usually hidden away in a case, it's not that important what you actually stick in there, right? But that's it for today. Thank you very much for watching. Please share, like, and subscribe. Leave a comment. I know that people are always very opinionated about these switching regulators, which I totally get. And I'm not an electrical engineer. I merely have a couple of tools to be able to roughly measure these things. And I do see from own experience that this thing here doesn't work in my 8050 and is probably not a good choice for floppy drives because it disturbs the analog section too much with its ripple. These are great for that application, but they produce a lot of heat, especially in the summer. In certain climate scenarios, it will be of a high risk to overheating and shutting down. Whereas these here are running really cool and have minimal ripple, so to speak, and will work most of the time. But again, that's it. Please check in for the next video, and until then, goodbye.